Hello everyone and welcome back to my channel. So in the last video we saw how we can set up Kaggle and get it ready so we can use it. In this video we are going to see the diabetic foot ulcer challenge dataset. We are going to see how this dataset looks like, what pre-processing steps we can apply on it, and how we can take this dataset and train our image classification model and then get results and basically get predictions on images and see how it will work. So to start off, as you can see, this data set has 4 different types or categories. I have added the images that belong to each category to give you an overview of how those categories look like so that we can work on them. As you can see, these are the 4 different categories. The first one is the none category, in which there is no infection and no ischemia. In the second one, you can see that there are a certain red regions that show that there is infection in it, and there are also some sort of grayish blackish sort of regions. But in ischemia, the difference is that we have more black region compared to the infection one. As you can see over here, the red is quite bright red and there is pitch black, that shows that there is ischemic infection in it. And then there is a category that is called both. This means that it has both infection and ischemia. So we are going to train a classification model that would be able to classify between non-infection and ischemia and both the classes. We would provide it with test images and see how our model would perform, and we are going to do all this using Kaggle. Okay, so our task is to start off by doing an exploratory data analysis on the dataset to see how the dataset looks like. Then we'll see what kind of pre-processing we can apply to the dataset and make sure that it is ready to be fed into the convolutional neural network for image classification. Once our model has been trained, we are then going to evaluate the model's performance based on different metrics such as accuracy, the F1 score, precision, sensitivity, specificity. There are so many measures that we can see. We are going to cover each and every step in the following videos, so you don't have to worry about it. We are going to see how we evaluate the model, what kind of performance metrics we use, why we use those performance metrics, and then we are also going to see what kind of predictions this model would provide on our test images. So without further ado, let's begin. First off, I am going to go on this DFU challenge website. As you can see over here, I'll add the link of this dataset website, this challenge website, on my video description as well. So if you want to check it out, you can definitely can. So basically in this website, you can see that there are 4 different challenges that have been going on since 2020. And this is the 2021 dataset because I was searching through Kaggle and I found a part of this data set on Kaggle, and I thought it would be much more useful for us if we can leverage that part that is already available on Kaggle, because you have to get access to these challenge data sets in order to start working on them. So I have taken this DFUC 2021 challenge, and if I scroll down a bit, you can see that we have different documents available. You can definitely go ahead and read through these documents. There are also great papers that have been published on this data set that would provide you a very good overview of how the data set looks like, what kind of work has already been done. And if you are looking for doing research on something like image classification, or you are working on medical imaging, this would prove to be very useful for you, I think. So as you can see, we have different things. For example, we have the challenge document, we have the dataset description. We can also apply for datasets. For example, currently they are working on the 2024 dataset, so you can definitely go ahead and see if you can apply to it and use it, and then definitely participate in the challenge in the future. So for example, if I click on this document, see, this website opens up, and if I scroll down a bit, this is the document that opens up. You can definitely read through this document and see what kind of data has been added and how they have distributed the data. So for example, here you can see they have 5955 labeled DFU patches. So what do we mean by patches? So if you search on Google, if I try to search ischemia for diabetes, for example, and I go on images, I can see that I get an image of the entire foot, right? That looks something like this, or maybe like this. So the DFUC people, what they've done is they have extracted patches so that the data would look something like this. You can focus only on the infected area or the area that has something in it, rather than focus on the entire foot, right? So this is what they have mentioned. They are working on a 5955 labeled patches, and then they also have unlabeled patches, and then there is data for validation and testing. Okay, so there is a lot of information that is provided about this data set that would provide you a very good idea of what it looks like, how we can work about it, and everything. So if I go back to Kaggle, I'm gonna go and hit home because we want to have a blank canvas to start working on. So basically, if I go to search and type DFUC2021 and hit enter, as you can see, I have this link to the dataset. I'll also add this link on the description below so that you can click on this dataset link and it will take you to the Kaggle link where the dataset is stored, like this. Okay, once we are here, as you can see that someone has already done a lot of work for us. They have uploaded a training data set patches. For example, here you can see there are 59554 for training, 5734 for testing, and 3994 for unlabeled patches. So as you can see, the dataset has already been uploaded. They have also given acknowledgement to the dataset creator or the researcher, Yap et al. So basically you can go through this data, and if I scroll down a bit, you can see that there are 3 different folders that have already been created for us. So we do not have to split the data set into train, validation, and test. It has already been done for us. So if I simply click on the train data, you can see that there are 4 different folders that have already been created. One is both, infection, ischemia, and none. Similarly is the case with the valid data set and the test data set. Okay, so now most of the work is already done related to splitting and everything. So to start working with it, we are simply going to click on this new notebook button. You can also definitely download this data set from here, and you can start working on it if you want on your own system. But if you want to leverage Kaggle, so you can definitely do that by clicking on this new notebook button. Once I click on this new notebook, as you can see, it has created a new notebook for us, and it has the data set already imported in it. These are a few lines that are used to set up the environment, the Kaggle environment for us, and it makes sure that the data set is loaded and everything. So before starting off, we have to first set a name for our notebook. You can set any name that you like. I'm going to set it like 2021 DFU dataset and maybe classification. Okay, this means that we will be working on classification related algorithm in this notebook. And you can simply next go to settings, and you can change the accelerator. I can select any accelerator based on your need or requirement. So I'm going to select this one because it allows me to do parallel processing, which we are going to do see how we are going to achieve it, right? So I'm simply going to click on it. This will provide me with this message that shows that availability is limited to 30 hours per week. When I start working on the code, I'll have 30 hours of time in which I can use this GPU. I'll simply click on turn on this GPU and it will start my session. Okay, so once my session will be started, I can simply click on this run button and it would run and load this data set for me, and I can continue working on it. Okay, so once we have loaded the data set and everything, we can start with our code. So these are the first few lines that are already provided by Kaggle. We do not need them, so I'm going to delete them from over here. Okay, so now our code begins. The first snippet of code is to load the data within the data set and see what it looks like, what kind of images we have, the count of images we have in each category. And basically, we're doing an exploratory data analysis on this data set before we start working with the machine learning model. Okay. So as you can see, if I click on this arrow button over here, I can see that I have the DFUC 2021 split dataset. Within that, I have these different folders, which is test, train, and valid. Okay, so I'm going to remove this path so that we can start with the clean slate. Our main aim for this snippet of code is to see how many categories we have within this data folder and how many images we have within each category. Okay, so here I'm just simply going to copy the path of the train folder and I'm going to put it over here. Okay, so you will find this data set details and code and everything in the description below. I'll add everything in the description so you don't have to worry about the codes. You simply just need to understand what needs to be done, how we navigate through different data sets, how we analyze them, pre-process them, and get them ready to be fed into the machine learning model. The aim of these videos is just to help us all understand what needs to be done when we have a data set and we want to do a certain task on it. So for example, in this case we want to do image classification. So as you can see, if I go into the train folder, I can see that I have these different images that belong to each of these four categories, right? So one thing that you can do is you can manually add the categories by like this. For example, I use this categories list and then I add the categories name manually. Another thing that we can do is we can dynamically list the subfolders that are within the train folder. This will help us to keep track. If we add any other folder in the future within this train folder, it would be automatically read by the code rather than having to manually add the categories over here. So we are simply going to use these categories and then we are going to use this os.list directory function, which would list all the folders that we have within this train directory, and then it would also check if these folders are actually folders or these are files. So for example, if this is a directory within this train, it would add it into the categories list. So for example, if I have this train folder, within this train folder it would go and check if I have this both folder. It would check if it is actually a folder. If it is, then it would add its name into the categories list. So this is how this line of code works. It uses the os.is directory function to make sure that it is a directory, and list directory lists all the files and folders that are within this train folder. Okay, the next line of code is to count the number of images that is available in each of these categories. So once we are done with reading all the number of images, we are simply going to convert the dictionary, which is this one. We are going to simply convert this dictionary into a data frame, and then we are going to display the image count based on the categories we have. So this is the output if I run it like this. As you can see, we have four different categories and these are the number of images that belong to each and every category. So one thing that I can observe at the very beginning is that the data seems balanced. So for example, if there is some category that has only 1,000 images, we can say that the data set is not balanced, because in infection we have 3,000 images, in both we have 1,000 images, and in none, for example, if we have 500 images, the data set will be highly imbalanced, which would create an issue when we are training a machine learning or deep learning model, because it would lead to model bias. Okay, so one thing that I have initially analyzed and observed is that the data seems balanced. The next thing that I like to do is, generally I like to display the images to see if they are loading perfectly and how the images look like manually. If we look into them and then analyze what are the contrast based differences, if we can differentiate them or something. So this is the code snippet for that. We have a plot images function that looks something like this, and within this we have this os.list directory, which is basically listing the category within this train folder. And then what I'm doing is I want to randomly display a few images to see if all the images are loading correctly or not. So the random sample function does exactly that. It loads random images from each of the categories within the train folder and it would display me those images. Okay, so here I can see I have this image.open function. This would allow us to read the images from the path, and os.path.join, basically what it does is it joins the category path and the image name. So for example, this is the category path we have, which is both, and this is the image. So it is basically joining this both path with this image name and then displaying it. So this is as simple as I can explain this code to you. I hope that you are coping up with it and you are finding it to be easier. So basically, if I just simply run it, it would take a few seconds. It could also take a few minutes depending upon the amount of data you have. So it has taken me a few seconds to load this. And here you can see I have these grid lines and these numbers over here, right? So we can also get rid of them by using this axis off. If we use this, it would basically load our images, but this time we do not have any numbers associated on the rows or the on the x-axis and the y-axis. We have a clear sort of view of the images in each of the categories. Okay, so now I can see that we have these different categories: infection, both ischemia and none. And if I try to look into the differences between them, in infection, I can see that there are certain yellow regions and there are also some red regions. And then in both is the combination of basically both ischemia and infection. So as you can see, we have blackish regions, red regions, yellow parts. Everything that you can think of is in this both category. It has gangrene sort of images and everything. In ischemia, we can see we have black looking pixels more compared to the reddish and yellowish ones. So this means that if an image has certain blackish regions, it means that it might belong to the ischemic region, ischemic categories. And then there is a none category in which there is certain swollen parts and everything, and there are certain white regions. But there are less black regions compared to ischemic infection in both categories. So this is basically an initial analysis of the data, but we just found out based on just manually visualizing them. Next thing that we are going to do is we are going to check the image resolution to make sure that the images in the data set have the same height and width. This becomes really helpful and useful when we are training machine learning model, because if you are training or you have trained a machine learning model, you might know that it requires a certain size of image. And if our data set has variable image width and image height, we have to resize them before feeding them into the machine learning model. And we have to make sure that if we resize them, we do not lose any information, and we are not, we want to make sure that the quality of the images remains intact or as good as possible, so that when it is fed to the machine learning model, it learns features much more efficiently and effectively. Okay, so for that I have used this check image resolutions function. The code is almost the same as the previous one, in which we were reading the image, in which we were listing the directory, and then we joined the category path, and then we use the image.open function to read the image. But this time we have this resolution list in which we are appending the image width and image height to make sure and to see what kind of image size we have in the data set. And then once we are done with it, we are simply using the describe function to see the details of the image breakdown and the image sizes and everything. Okay, so this is the output that we get. So here you can see that the total number of images that we have is 12,604. The mean width and height of the images is 224, 224, meaning that we have images that are of the size 224 into 224 in the data set. Next, the standard deviation is 0, meaning that the images are of the same size in the entire data set. If the image resolution is varying within the data set, the standard deviation value will be changed. So this would provide us with an indication if the data set is of the same size or not. Next, we have a further analysis of it, in which we can see that the minimum is 224 into 224, meaning that the minimum resolution within this entire data set, combining all the categories in the train folder, is 224 into 224. And then these are the quartile ranges. So for example, the first quartile, we can see that around 25% of the images are of size 224 into 224. Then the median is, or the 50% is 224 into 224, meaning that around 50% of the images are exactly of 224 into 224 resolution. And then the 75% shows us that 75% of the images are of the size 224, 224. And then maximum shows us that the maximum resolution within this data set that it has detected is 224. So this provides us with a good idea of what kind of resolutions we can expect and what kind of processes we can do further. Okay, so here we also have a category wise breakdown in which we have the count of images in each category, and then this is the mean standard deviation. As we have discussed earlier, this provides us with a good overview of what kind of image size we can expect in each and every category. You can definitely use them in other data sets that you are using, and it would provide you with a very good idea of what kind of data you are working with. Okay, so the next thing that we can do is to see the pixel density distribution. As we can see over here, the size of the data is pretty much the same for all the categories and in each of the classes, meaning that this data set has already been pre-processed in some way, and someone has stored it in Kaggle so that we can use it. So most of the work has already been done pre-processing wise. For example, if we do not have a same resolution size over here, we have to go through some additional steps to make sure that our data quality remains intact and we can use it. So next thing that I can think of on top of my mind is to see the pixel distribution. Pixel density distribution provides us with a good idea of how the pixel intensities are distributed among the image, so that we know what to expect and what kind of steps we can perform to make sure that the data is normalized. Okay, so if this is basically the code for pixel density distribution. We are reading the image, we are making sure that the images are present, we are using the image.open function to reach the image, and then basically we are plotting this histogram to see how the values are distributed for each of the images. For example, in the infection category, we can see that the pixel values are distributed something like this. In both and in ischemic category, we can see that the image densities are distributed from the very beginning to the end. So for example, in histogram, we have a range of 0 to 255, meaning that 0 shows us with the black region, or the background represents the blackish sort of region, and 255 represents the brightest pixels. Okay, so if we look into the histograms for each category, we can see, for example, in the ischemic region, we can see that there is a lot of spread of intensity values, meaning that there is a lot of contrast difference here. So the amount of values that we have are quite high for contrast, which means that there is more variability in the pixel intensity. This basically leads to greater texture variation, meaning that the texture varies in all of these categories. This is very good for us because we can see that there is certain contrast differences, and this can be very helpful when we are working with a machine learning model, and we can focus on the ones that are basically specifically designed for contrast based feature, and they take into account those and then provides us with a prediction so that we can better train our models. As you can see, the data spread, the intensity spread shows us that the intensity values are very much spread from the start to the end. Okay, so if I go further and I try to visualize them and see them mathematically, based on the values that we get, to get a better idea of how the intensities are distributed, I have used this. For example, this is the function that we have used in which we are mathematically trying to see the contrast value. The code remains the same as the previous one, but this time we are displaying the contrast distribution by category and everything. Okay. So here, as you can see, we now have a box plot, and we also have these counts over here. So as you can see, we have the amount of images that belong to each category. Next, we have the mean intensities for each category. And if you try to observe this, you can see that for both category and the ischemia category, the mean intensity are very much closer, meaning that these have pretty high contrast compared to the infection and none category. If we look at the standard deviation, it shows us with almost the same statistics, where the standard deviation for ischemia and both is greater compared to infection and none. And this is basically the quartile based interquartile range, 25%, 50%, and 75%, which provides us with a good idea of how the intensities are distributed among different categories. So in order to better visualize this is a box plot. In this box plot, first let's understand what all of these things mean, so that we have a better idea of why we have plotted this box plot and what kind of insights we can get from it. So if I go over here, you can see, okay, so you can see from here, if this box region has lower quartile and upper quartile, and the midline, which over here in this code is green, is basically the median. So this is 25% interquartile range, this is 50%, and this is 75%. Okay, this blue line that you can see over here is called whiskers, and this is the minimum range of the whiskers. This black sort of vertical line, horizontal line, sorry, is basically the lower range, and this is the upper range. Okay, so if we try to read this, we can see that the box basically is showing the interquartile range, and if we compare all these boxes, we can see these two boxes are above these two, meaning that the interquartile range of both in ischemia is higher compared to infection and none. Next, if we try to see the median, this green line over here, we can see that the median is also higher for these two classes compared to the infection and none. Next, if you look at the whiskers, and it ends over here, the upper range of the whiskers is over here, and these outliers are above the whiskers, meaning that there is significant contrast difference if the outliers are above the maximum range of this whiskers. Okay, I hope that you are understanding what I'm trying to say. Okay, so basically we have these outliers, and if we try to compare these outliers of these four categories, we can see that the ischemic category outliers are highest compared to the other categories, and the lowest one we have is for this none category. So this provides us with some idea of what kind of contrast distribution we have based on the different categories, and we can understand based on the mathematical statistics and visually analyzing it and seeing the histogram that there are certain contrast differences in this data set. Next, another thing that we can do is that I found to be really interesting was to do this ANOVA test. This ANOVA test provides us with a confirmation sort of thing to make sure that we have contrast varying among categories or not. So this is just these are just basically mathematical ways to show the other person, or to make sure that we have statistical differences in contrast and everything, and we can prove it. If we are claiming something, we can also prove them mathematically and statistically and visually, so that the other person could understand what we are trying to convey. Okay, so for all these categories, if we try to print the statistics and the p-value, we get the p-value of 0.0. If the p-value is below 0.05, or if it is 0, it means that there are contrast differences or significant contrast differences between the categories. Next, if we have for example, the value of F statistics is this. This means that we have some variation among different groups, and we have a high S statistic. That means that it indicates a large difference between group means relative to the variability within each group. Basically, all this analysis means that we need to do some sort of preprocessing to make sure that a contrast is normalized, so that when we feed it to the machine learning model, it gets a better idea of the features. And if we do not normalize the contrast, and if we provide the data as it is, I don't think it would provide us with good results. So this is what we have done so far in terms of preprocessing, and we have decided after our exploratory data analysis, we have decided that we can apply contrast normalization to our data set. So to apply this contrast normalization, we have gone through all these steps. Basically, we have a lot of things that we can do when it comes to preprocessing, but we have to make sure that we can, that if we are applying them to a certain data set, we need to make sure that they can be applied, or they should be applied. There should be some reason behind those preprocessing steps. So the purpose of this entire exploratory data analysis was to make sure what kind of steps we can perform to get our dataset ready to be fed into the machine learning model. So based on the analysis, we come to a conclusion that we have to apply contrast normalization. And for contrast normalization, the best normalization that I have come across so far is the contrast limited adaptive histogram equalization. What it does is it applies local adjustments to the data, and it makes sure that it preserves the preserves more detail while it is normalizing contrast. So for example, if I type over here, we can also see how the contrast limited adaptive histogram equalization looks like. So as you can see in this image, this has been a contrast limited adaptive histogram equalized, and as you can see, it provides us with much more sharper detail compared to this image. Okay, so coming back to the code, here is the code for this. Now simply in this code, what we are doing is we are applying the preprocessing using the OpenCV library. We are using this create clahe function, and then we have the clip limit and the tile grid size. Tile grid size, make sure that we are taking an 8 into 8 matrix and we are convolving it to apply the contrast limited adaptive histogram equalization, and then clip limit of 2 makes sure that we are applying enough equalizing, but we are not going too far with it to make sure that the details are preserved. Next, we are going to create a custom data set to load these images. All this code part is to make sure that we are getting our data ready, and for this I am using PyTorch because it allows me to use parallel processing. As we discussed earlier as well, I have these 2 GPU over here. I use the accelerator, which is GPU T4x2, and provided me with 2 GPUs. I want to make sure that I make the most use of both of these. So for that, I'm using a PyTorch because it provides us with much easier and effective way to utilize the GPUs that we have in our system as well as on Kaggle. So, okay, so in this code snippet, we are just using a dataset, a custom class to load the images, and then we are applying transformation on them. All this data is provided in the description below. You don't have to worry about it. And also, one thing that I would like to suggest is that if you do not understand some code snippet, you can simply copy it and give it to ChatGPT or Perplexity, and you can simply understand what this code is all about. You don't have to understand each and every line and become a coder. You just have to make sure that you know the logic behind the code that has been done, and you can make other people understand it, and you know exactly what is going on in the code snippet. Okay, so in this code snippet, we are simply, what is being done is that the categories are being defined as we have done earlier as well. It is going through dynamically, going into each of the folder, and then it would go and read the category names and images and enumerate them. And then also another step that it is doing is it is doing mapping, label mapping, which means that it is labeling or enumerating each category rather than using both infection and ischemia and none. It is giving it an integer value. So for example, for both we have 0, for infection we have 1, and so on, for example. So next thing we are doing is we are looping over each category to get the image path and label, as you can see over here. Next, we have this definition of length, which provides us with the total amount of data we have. This get item, what it does is it takes each and every image from each and every folder, and then what it does is it splits the channels RGB because these are colored images. It is splitting each channel, and then we are applying the Kalahi filter on each and every channel separately and then combining it. So this is the entire code for that. And finally, we need to define any transformations we want to apply. So for example, if we are applying data augmentation, we can use zooming, we can also use sharing, randomly flipping and everything. You can definitely go on and experiment with those steps. For now, to keep the code very simple, I have just added this resize function. Our data set is already 224 into 224, but we have to reinforce this over here because certain machine learning model, for example VGG16 model, requires your data set to be of size 224 into 224, right? So if there is a certain requirement of some model to have a specific image size, you can definitely go ahead and change this transforms and then add your image size here. So for example, if you want 512 into 512, you can add it over here. If you want 299 299, you can add it over here. Next, it is transforming or changing it into a PyTorch tensor. Because we are working on PyTorch and we want to train our model using PyTorch, we are converting it to tensors because PyTorch works with tensors. Next, we are normalizing the image. or normalizing the RGB values. Okay, so once we are done with it, the next step is to create a data generator, right? So to create a data generator, we are simply going to instantiate the data sets for train and validation. We have these three variables over here, and as you can see, we have these three paths over here, right? We are simply going to copy these paths, paste them over here like this. Same goes for the validation and test set. And once we are done with it, okay, so once we are done with it, we are simply going to call this DFUC custom data set that we have created, that is over here. Okay, what it would do is it would go into these folders and read the images, and then it would place them over here. And this transform is equal to transform is this function in which these transformation will be applied to the data. First, it would apply the Clahi filter based on this function, this custom class that we have defined, and then it would also apply transformations to the data set. Next, what we are going to do is we are going to use the data loader to create mini batches. Mini batches allows us to save memory, and it would help us to use larger data sets. So what we are trying to do is for each epoch, it would take batch sizes of 32 until it iterates over the entire data set for one epoch. Okay, so number of workers over here are 4 because we are using parallel processing. I have applied it over here like this. Um, okay, so you can also better understand this. You can go into the documentations of each and every function and functions and everything, and better understand this. Why we use mini batches, why don't we use the entire data set at once, is because the memory would run out. So we need to make sure that we have enough memory and we do not put too much load, and we also want to make sure that our model doesn't overfit. So to make sure that we do not overfit our model, we need to use mini batches. Okay, so once we are done with it, the next step is to finally visualize the data set to see what kind of separation of data we have, and how many images we have in each category, what kind of data split we have created. In this code, I haven't used dataset split because the dataset has already been split into test, train, and valid folder. If you only have this folder and it doesn't have any data train and test split, we have to use the data split function in order to create a random split of data. And then we also need to make sure that we have that for example, if data is patient based, we have to make sure that one patient is not repeated in both the test and train folder. So for that, we need to use different strategies. We are going to use them in other projects that we are going to do, but for this project we already have the train, validation, and test split, so we are not going to do that. Okay, so finally, if we display this, we can see that we have, for train data distribution, we have 3066 images for none. For validation, we have 1022 for none. And for validation, sorry, it has been repeated over here somehow. Let me change this. Okay. Okay, so for test data distribution, we have around 511 images for none, and so on. So I also like to do a sort of a sanity check to make sure that everything is going okay and the contrast normalization that we have applied has been applied correctly. So for that, I have also used this function to display the data, some random images from the train, test, and validation generators. So as you can see, it looks something like this. We have converted a category into numeric values because this is how our machine learning model would work. And this is the validation dataset images, and these are the test dataset images. Okay, so now our data set has been prepared. We have preprocessed the data set, split it into train and validation and test set, and then we have also created the data generator. The next, what we are going to do is we are going to simply use our machine learning model and then start training it on the data set we have prepared.